Now we will move to the second part of our lecture. We have discussed environment and AI agents in the environment. Now we will look at search. Talking of search, we have two kinds of search, uninformed search and informed search. The difference between the two searches is that in an uninformed search category, the algorithm knows nothing about the domain and it just forms a simple strategy irrespective of its environment. In the informed search, however, there's an additional information about the environment that helps the algorithm optimize its answers or search results. Informed search, a search strategy that uses problem specific knowledge to find solutions more efficiently. Uninformed search is a search strategy that uses no problem specific knowledge. There is another form of search called greedy best first search. It's an algorithm that expands the node that is closest to the goal as estimated by a heuristic function h to n. Search. Now, why do we need search? Simplistically speaking, you need search when you're playing a game, such as moving tiles game or a tic-tac-toe game or a chess game. When there are all kinds of options available, which one should be chosen? There has to be some strategy behind it. Obviously, you can do it randomly, but that will not bring any intelligent result out. So, to achieve your goal, which in this case is ordering the tiles and numerically, in any of this kind of goal seeking objective, you perform search. Again, the example of moving and traversing through maps, you need to do search and find out the best results for reaching your destination. For search problems, we need to get comfortable with a certain vocabulary. And one of those things is agent. We know by now that agent is an entity that perceives its environment and acts upon that environment. State is a configuration of the agent and its environment. With every action taken, the agent changes the state. So, for instance, so where do we start from? Wherever we start from in that environment is the initial state. Actions, those are the choices made by the agent to change itself from one state to another state. Actions returns the set of actions that can be executed in state S. Now, in a certain state, for example, the action can be moving right or moving left or moving upward or moving downward. Transition model is a description of what state results from performing any applicable action in any state. Transition model returns the state that it has resulted and the action that caused the resultant state. For instance, if this is the state of our moving tile game and we take the action of moving this tile, the last tile, which is closest to the empty slot to the right, then what we will get is this state. So this state and this action of moving the tile to the right has transitioned the state to be this. What was the other possibility? Over here, there are only two possibilities. Moving this slide number 15 to right or moving slide number 12 downwards. So if we take the second option, a second of the two options available, and we move the tile downwards, then the resultant state is this. Now look at it. Every result which is starting from the same state is causing a different resultant state. Transition model is encapsulates all of these things. The result caused by an action performed on a state. What is a state space? The set of all states reachable from the initial state by any sequence of actions is called a state space. So for a binary one space environment, our state space will be null. Null set is always part of the state space, and then a possibility of a 1 or a 0. But let's say there are two positions for binary options like the data is binary and there are two positions for it. Then our state space will expand to a null state, a 1-0 combination, a 0-1 combination, an all 0 combination, and an all 1 combination. So over here, in this example, the state space of this state is both of these states, because all the possible options from here onwards include this position and this position. So again, looking at this example, the state, the states, sorry, this has to be sample space. The sample space of this state includes this and this, and there's always one move that will bring it back to this state. The sample space of this state includes these two options, and this is how it keeps on growing. The sample state of this includes two options because there are two moves, sorry, three, because there are three moves possible. And this is how the sample space is, it grows exponentially. Goal test is the way to determine whether a given state is a goal state or not. Path cost, it is not included in the uninformed search, but in an informed search, the path cost is a numerical cost associated with a given path. So for instance, moving from C to D has a cost 1, and moving from C to A has a cost 2, moving from C to H has a cost 3, which means that moving from C to H is the most expensive decision to take. Search problems define initial state, the point to start from, the actions that can be taken, the transition models that result from taking those actions, the goal test, just to realize if you have reached the goal and stop, and in a case of informed search, path cost function. Solution is a sequence of actions that lead from the initial state to a goal state. Optimal solution has the lowest path cost among all solutions. Frontier, it's also called fringe. Frontier is the unexplored nodes from the last explored node. So for instance, if you are at 15, you have explored all the nodes from 1 to this part, 1, 2, 4, 8, 15, and you have not explored further, then the frontier includes one node. However, if you have taken the path 1 to 2, to hopping to 4, to hopping to 8, to hopping to 16, and now you have stopped here, the frontier is actually these two gray paths, gray nodes, which are actually diverging from 16 to two different paths. Node. Node is a data structure that keeps track of a state, a parent, an action, and a path cost. Approach. So you have to start with a frontier that contains the initial state. No matter what algorithm you're using, you repeat that if the frontier is empty, then there's no solution. And you keep removing a node from the frontier. If node contains a goal state, then that is your solution and you stop. If the goal state is not reached and we have not reached the end, the frontier still exists, then we keep expanding. Now, when we expand, this is where we use some strategy of search to expand in a certain way or traverse in a certain way that will give us better results than going to every possible set one by one, going to every possible node one by one. Uh, when we reach here, for instance, at this point, there is no more frontier, which means this is the last node for this path. The last nodes are called leaves, also child nodes. Now we look at breadth first search, which is one of the most simple search strategies in AI. A breadth first search is an algorithm that always expands the shallowest node in the frontier. If we look from the perspective of data structure, the breadth first search is a first in, first out data type. Let's look at this simple example and traverse it through breadth first search. Now, In breadth first search, we need to define the convention if we plan to move left to right or right to left. And we have to keep the convention uniform throughout the traversing of the tree. In this tree, if our start is A and our goal node is E, then we can see that at the top level, at the first level of breadth, we only have A. At the second level of breadth, we only have B. At the third level, breadth-wise, we have C and D, two frontiers. And as we move down, the last and the deepest part of the breadth first approach will include E and F. Let's say we also plan to move left to right. The first time that we move our frontier, first time that we start, our frontier is A. Then moving to B, we have explored A or visited A. So we place A over here and move to B. Now our frontiers are C and D. From C and D, because we have declared our approach to be left to right and C is the leftmost, we go to C, we declare it as explode set, and now we have the frontier of C. Earlier, I had told you it's a queue format, a first in, first out format. So when we move from frontier to the visited set or explored set, we take out from the top. But when we have to push or enqueue data into the structure, we do it from the tail, which is a first in, first out format. At C, we have still not reached the goal and we're moving left to right breadth-wise. So the next node is D. Once we reach D, we will know that our frontier is F. Now, if you notice, our goal is E and E is already in the frontier. However, we have not reached the E, which means that the explode set does not contain the goal node. Therefore, we will put F in the frontier. However, when we reach E and E is joined in the explode set, we will have our results, and that is where the goal is reached. So we don't move any further and stop right here.